when you, after you graphically shape it, you are gonna automatically add 2 or 3% to that, because I bet you anything, if you would add another 0.5% of water, you probably would have improved it. You're looking at me like, oh shit, I took the peak as my peak. It's not. You understand how this works?
Should the optimum moisture be pretty close, probably within 0.5% or so,
Yeah.
between the standard and modified?
Um,
Because the soil characteristics would still be the same.
Well, but
Saturation,
again, maybe the standard would probably have a little more water in it, but it would be, yeah, the soil will be the same type of characteristics. Yes, it should be similar, but it's not, because these curves sometimes are like this. You know what I mean? So this now is down here. Okay. You know, we'll see from the results, and then I'll comment when I look at your.
Because I know on mine was within 0.5%
Yeah,
moisture.
it makes sense.
But, you know, once again, it depends, I think, how you plot it.
How you plot it, yeah, exactly. So it should never be, your highest value should never be your maximum dry density and your optimal moisture content. It's impossible that you know, just by mistake, you got the right point. So anyways, so last week we did, the proctors, which modified the standard proctor. This week, we're gonna take this information and we're gonna reverse engineer it. So this week, what we're gonna do is we're gonna find the density of an area that was already compacted. So, let's assume that we're building a road, and this road has been compacted. Now, we do have our curve that describes the soil, so we already are aware of how that soil behaves under laboratory conditions, right? Because we did a proctor. So we know that the soil is gonna need so much moisture in order for us to achieve that type of, ideal compaction. So today, what we're gonna do is we're gonna evaluate a subbase, and we can make an assumption that it would be a subbase for a road, let's say. And we're gonna evaluate it by, we're gonna compact it, and unfortunately, our compactor is behind a cage, so we're gonna do it manually. So we're gonna take some soil, we're gonna build a pit out of blocks. We have blocks out there. We're gonna fill it up with soil, we're gonna put water in the soil. We're gonna put the percentage of water that you guys came up last week, 8, 10, 12%. And we're gonna compact it using a block, okay? We're gonna put it in layers, maybe 2-inch layers, and we're gonna try to do our best. All right, we need about a 6-inch, compaction, 6-inch layer, of soil. And then at the end of we're gonna disassemble it and put everything away. Normally, we would use a nuclear gauge to evaluate the soils after it was compacted. Today, we're gonna make the assumption that we do not have one, and we're gonna go back to more rudimental ways of finding out the density and the moisture content of the soil. And we're gonna, in order for us to do that, we're gonna use what is called in the industry a sand cone, okay? And a sand cone is one of my favorite labs, and you'll see why, because it makes sense at the end. And whoever came up with the sand cone idea, I think was a genius, because by doing a sand cone, you can figure out the density of soil, not knowing too many things that belong to that soil. And I'll explain what I'm talking about. So for example, one way of doing this would be, also, if possible, would be to add water to the soil. And I'll explain in a second, actually. So for example, let's say this is our compacted soil, Right, we gotta find the density of how well compacted the soil layer is, right? So we know that density is equal to mass over volume. We know that, right? So let's say I dig a hole here, right, with a little scooper, and all the soil that comes out of there, I put it in a container, and I know, you know, the weight of the container, right? So I make a hole, right, nice and chisel, and I put it in a container. And I weigh it, that would be my mass, right? But the question is, how would I determine the volume of a hole that is not perfect in shape? It's almost impossible. One way to do it, if that was a sealed area, I can fill it up with water, right? And then depending how many liters or how many gallons of water I'm putting in that hole, I can figure out the volume doing it that way, right? So if a gallon went in there, then the volume would have been a gallon, right? But because it's soils, if I put water in there, I'm gonna lose it. So the other way to do it is by using a sand comb. And a sand comb, which I'll get in a second, apparatus, has, kind of looks like, it's a brass, it has a brass cup at the end and a bottle attached to it, full of sand. All right? So the way we do this test, which is pretty simple, is the first thing we're gonna do is we're gonna find out the density of the sand inside the sand comb. And the way we're gonna find out the density of sand is basically we're gonna fill it up with sand. We know the volume of the bottle, right? It's actually labeled. We're gonna weigh it. Loose, we're gonna do loose sand. So we're not gonna do approximate. We're gonna weigh it. And then we're gonna do the mass over the volume, that's the density of the sand. Make sense?
Mhm.
So that's known. So density of sand, this thing I lost the point, the one inside, is equal to a value that we know. Right? All right, so this is where the math comes in. So we know the density of the sand. So now, what we're gonna do is, we're gonna, by experimentation, we're gonna open up the valve. There's a striker plate that we put it in. Not a striker plate, it's just like a base plate that we put it in. So by testing, we're gonna open up the valve. This is gonna be on the desk or inside a pan. And we're gonna figure out how much mass goes into that bell-shaped cone. Right? So what we're gonna do is, we're gonna have a pan, we're gonna put the base plate on, we're gonna open up the valve, and we're gonna wait for the sand to stop. It almost looks like an hourglass. You can see through, it's translucent so you can see through it, and you're gonna hit it very lightly with a pencil every once in a while, and you're gonna see the sand just going down, going down, going down, and then at one point it's gonna stop. When it stops, we're gonna close the valve, we're gonna pick it up, and we're gonna weigh it again. All right, we're gonna do it a couple times so we know how much mass we're losing inside this cone. Okay? Okay, so that's, now we know exactly how much mass we need to deduct at the end. All right, so when we're ready to do the sand cone, we're gonna put the base plate on the sand. This is now in this, over here, we're gonna put, which it has a circle in it. So we're gonna put it right on the sand. We're gonna grab a, some type of device that we can use as a shovel, like a spoon. And very gently, we're gonna pick up and put it in a container that we know the weight, right? And we're gonna make a hole. In the book, it tells you pretty much the dimensions of this hole that needs to be for the accuracy, right? So we're gonna scoop it all out and we're gonna make that hole, right? We're gonna weigh that mass, and that's gonna be our measured mass. And this density here is gonna be the density of our compacted layer. So that's gonna be the mass of sand. Right? Okay, we need to know the volume. How can we figure out the volume at this point? One second. Remember, we know the density of the sand. So the density of the sand, we have a number, 100, let's say, pounds per cubic foot. And this is equal to mass over volume. It's known, right? So let's say, and remember the volume is a constant. So we dig the hole, we take it out, we know the mass of the sand, right? So we gotta figure out how much volume went into that hole.
So you put the,
So what we do is, yeah, okay, go ahead.
you put the sand from the sand cone thing in the hole that you
Yes.
just dug out.
Yes, so what we do is we put our apparatus here. We open up the valve, and we're gonna fill this with sand all the way into the cone. Right?
And you subtract out the cone, that's why you need
We're
to
gonna
know.
subtract the cone because we measured it previously.
Yeah.
So now we know exactly how much mass of sand went inside the hole, right? So let's say that the density of sand is 100, make this assumption. So we're gonna say 100 is equal to the weight of sand, which we're gonna know what physically it is because we're gonna weigh it. And this is also known, divided by a volume that we don't know. So we have two knowns and one unknown. So we multiply the volume over here, and then we divide by 100. So the volume is going to be equal to the weight of sand divided by the mass of sand. You get it? So now we have the volume. We go back now. Now remember, the soil that came out of here, right? We're gonna save that in a container. We know that weight now, right? So basically, we're gonna go back and we're gonna figure out the density of the compacted soil. Which is equal to the weight of the soil removed, not the sand, divided by the volume that we calculated with the sand cone. That takes care of a density. Next thing, we take a sample of soil, like we did last week, and we figure out the moisture in the sand. We compare that to our Proctor curve, and we can tell the contractor whether to add water, or if there's too much water, or if he's within the specs of the contract. Let's say it was 95% compaction. Matt?
No, so I was just about to ask, so why do we need to know this? That's the reason we need to know this?
We need to know this because a contractor comes to your site and he's gonna put soil down for a base, for a building, for a road, whatever it is. And he rolls it with a big, roller, and then he's gonna turn around, he's gonna say, is that enough compacted? You can't just look at it and say, yeah, it's enough. You're gonna look at your Proctor results, right? So you know what the maximum dry density is. And then you need to figure out the density of the situ soil, the soils that they just compacted. Normally, I guess, again, this, by the way, the Proctor gets done no matter what. We use that today, every day. Sand cone is not something that you use every day because it does take a little longer to do. You know, we're gonna be actually studying about, you know, the nuclear gauge. I'll show you a video. We don't have one here in college. And remember the reason why we don't have one? We don't have one because it takes a special license to be a holder of one. And if we did have one, you guys would not be able to use it. Because you have to be specially trained and you have to have a license to use it. I think the only person in this room that probably has a license, you're probably expired, right? Or you still have it?
It doesn't explain.
It doesn't expire? So the only person, I don't even have a license as a teacher. But, you know, would be, if I had one, Eric would be the only one that can demonstrate it at this point. It's illegal for anybody to touch it except a licensee. That's why the college doesn't want the liability. But we'll show you a video on it. But in lieu of that, the next best thing to do would be to do a sand cone. I actually have done a couple of projects using sand cone. It's a little bit of a pain because it takes longer. We had to have some Bunsen, fire out to dry out the soil, the moisture content. But it's feasible. It's not impossible. This test here should only take us, once we have the machine calibrated, the sand cone calibrated, so we know the density of the machine, we know exactly how much weight goes into the cone, then the whole test should take 5 minutes. All right, so what we're gonna do is we're gonna divide in two groups. We're gonna have one group that's gonna prepare our testing facility, grab some blocks, and then we're gonna have one group that is gonna calibrate the sand cone, okay? We're gonna use play sand in the sand cone. It has to be dry sand, because it has to be the type of sand you would put in an hour. What? Hourglass, yeah, I couldn't come up with the word. So you want it dry and you want it to flow freely. We're gonna calibrate it. We're gonna find out how much mass goes into the cone itself. So we'll do 2 or 3, different runs of it. And you don't have to fill it up every time. So we're gonna fill it up once. We're gonna put it in a pan, with the base. We're gonna open it up, and you can kind of use a pencil mark, and put a pencil mark on the plastic. And then if you're below the pencil mark, it's still going. It takes a few minutes for it to stop. Once it stops, close it, weigh the sand in the pan, put it back in a bucket, put the thing back on, weigh again the sand cone, because now it has a different mass because you took a bunch of sand out of there. You can redo it. You can probably do it up to 3 times before you run out of sand in the sand cone. All right, and then as long as that your 3 numbers make sense, that means you did it right. You average them. That's the average weight that goes in your sand cone. So what I'm going to do now is I'm going to see if I can find a video on YouTube to show that. Any questions?